Welcome back to the deep dive. If you've ever wondered why some really high-strength metals sometimes fail catastrophically right when they should be at their toughest, well, you're in the right place. Today we are diving deep into the microscopic world of material science, specifically steel heat treatment.
Yeah, and how we make steel tough, but also the surprising way those very treatments can backfire.
Exactly. We're looking at something called tempered martensite embrittlement, TME for short.
We're exploring TME. It's a really foundational problem in metallurgy, actually.
Why foundational?
Because it happens right in the middle of the heat treatment process, the very process that's designed to maximize toughness. It's quite counterintuitive.
Fascinating. So you put this through all this effort, quenching, tempering, and the process itself introduces a potentially fatal flaw. What's our mission today?
Okay, so our mission is to really dissect a cornerstone piece of research. It focuses specifically on TME in low alloy steels.
Low alloy steels, okay.
And we're aiming to move past the more general theories, you know? We want to zero in on the microstructural roles of two specific things, retained austenite and cementite.
Right, trying to pinpoint exactly what causes this loss of fracture toughness.
Exactly. It's really an investigation into how the microscopic structure dictates the material's destiny, its macroscopic performance.
Okay, let's start with a clear definition then. What is TME? What's the observable problem we're talking about?
So TME is basically a sharp, very localized reduction in fracture toughness.
Okay.
It happens when you take these quenched low alloy steels and you temper them, typically in the range of about 300 to 500 degrees Celsius.
And that's the weird part, right? You expect tempering to make it tougher.
You do. You expect it to become tougher, maybe a bit stronger as you temper it.
Yeah.
But in that specific temperature window, performance just, it falls off a cliff. The steel becomes surprisingly brittle.
Wow. Okay. Now, before this particular research, what was the thinking? What was the standard explanation for this dramatic failure?
Well, the historical debates sort of had two main camps, but honestly, both were pretty generalized.
Like what?
Some people attributed TME to impurity segregation.
Yeah.
You know, where unwanted elements kind of clump together at the boundaries inside the steel.
Right, making weak spots.
Exactly. Others just blamed a generalized sort of wide-scale precipitation of carbide phases throughout the structure. But the researchers we're looking at today, they felt those explanations weren't quite specific enough.
Not specific enough to explain why it happens in that temperature range.
Precisely. They couldn't explain the exact temperature dependence. So they decided to look closer, really zoom in on the structure itself, specifically at the lath structure.
Okay, we're immediately hitting some jargon there. When you talk about the lath structure, what are we actually visualizing inside the metal?
Yeah, good question. So when you quench steel very rapidly, it transforms into a phase called martensite.
Okay.
But this martensite isn't just one solid block. It's made up of extremely fine, almost needle-like features. We call them laths. Think of it like a huge bundle of microscopic needles packed incredibly tightly together, and where these tiny needles meet, you have boundaries.
Got it. Almost like a dense fiber composite, but it's all steel.
Sort of, yeah. That's a decent analogy.
And to study TME, the researchers focused on one specific candidate alloy, an iron-carbon molybdenum steel, specifically F4Mo Deardel 0.2C. Why that one?
This molybdenum alloy is crucial because after the initial quench, it retains a measurable amount of something called residual austenite, about 5%.
Residual or retained austenite. Okay, so that's our first main character here.
Definitely.
And what exactly is retained austenite? Is it just leftover stuff?
Pretty much. It's the original high-temperature phase, austenite, that should have transformed into martensite during the rapid cooling during the quench. But it didn't quite finish. So it often sits there as these very thin, often unstable films right between those martensite laths we just talked about.
So it's stuck between the needles.
Stuck between the needles, exactly. And previous research had already kind of hinted that TME in this specific VMOC system might be fundamentally tied to what happens to this small amount of unstable retained austenite.
Okay, so the central question for this experiment then becomes, is TME controlled by the instability of that 5% retained austenite? Or is it caused by the formation of these ultra-thin cementite films? And if it's the films, how are they actually created?
They were looking for the exact chain reaction, what kicks it off.
All right, let's move from the theory to the actual performance.
Yeah.
When they tested this VMOC alloy, How did this TME thing show up on the macroscopic performance charts?
Well, the results from the impact tests are really visually dramatic. You look at the graph.
Yeah.
Toughness, which they measured as impact energy, showed this massive dip, a huge drop. The minimum impact energy, which means maximum embrittlement, occurred right around the 300 degrees Celsius tempering temperature.
So it's not a gradual decline, it's a sharp drop.
Exactly. It's not a slow trend. It's a sudden, really sharp, localized nosedive in performance
Yeah.
right in that window.
And what makes that so surprising, I guess, is that the overall structure should be getting softer, maybe slightly tougher as you temper it higher.
Right, precisely. And that's where you have to look at the contrast with hardness.
Okay, how did hardness behave?
Hardness showed a steady, continuous decrease as the tempering temperature went up, from the as quenched state right up to 500 degrees C.
Just getting progressively softer?
Yeah, just general softening, which is exactly what you'd expect during tempering.
So this is a really critical distinction then. The generalized overall behavior, the softening happens across the whole temperature range.
Right.
But the catastrophic failure, the drop in toughness, only happens in that narrow, 300-degree window.
Exactly. It's a huge signal that the mechanism causing that minimum toughness is highly localized, it's extremely temperature dependent, and it must be chemically distinct from the general processes that govern the overall softening.
So TME isn't just general fatigue or wear.
Not at all. It's a specific structural failure triggered by a very particular narrow phase transformation event happening inside. We have to go back and look at those laths again.
Okay, let's zoom back in then. We know this retained austenite, the RA, is unstable, and it sits in those thin films between the martensite laths. What happens to that RA when the steel hits that critical 300-degree temperature range?
Right. This is where the real detective work happens, using transmission electron microscopy TEM. That was the heroic tool in this research.
Allowing them to see these tiny structures.
See them directly. So we already established these thin RA films are prone to transforming, right? And that transformation itself creates stress, imposes constraints on the surrounding martensite laths.
Okay.
The theory was that the products of that RA transformation and what it turns into are the true culprits behind the embrittlement.
And what did the TEM show? What was that specific transformation product?
It showed intralath cementite precipitation.
Cementite. Okay, define that for us.
Cementite is essentially iron carbide, F3C. It's a very hard but also very brittle phase found in steels.
Right?
And they found considerable amounts of this cementite precipitating out. But crucially, this cementite wasn't just random blobs. No, it adopted a specific crystallographic orientation relationship with the martensite matrix surrounding it. It formed a highly organized structural film right along the lath boundaries.
We should probably pause there because this sounds like the core of the failure mechanism. Cementite is naturally brittle, we know that. But why is it so destructive here, sitting as a film between the laths? Is it the amount or the shape and location?
It's primarily the location and the morphology, the shape. You see, if cementite forms as, say, rounded globules dispersed within the steel, the material can sometimes absorb energy by deforming around them.
Okay, it can kind of flow around it?
To some extent, yes.
Yeah.
But here, the decomposition product, this cementite, forms these incredibly small, discrete, almost continuous films right along those boundaries between the martensite laths.
Ah, so like thin sheets.
Exactly. And
Yeah.
these thin, brittle sheets act like pre-existing microcracks. They're just sitting there waiting for a stress to exploit them. They provide an easy path for fracture.
So just to recap the chain reaction for this specific steel, the unstable retained austenite is the chemical trigger. It decomposes around 300 degrees C, and that decomposition creates this brittle cementite film along the lath boundaries.
Correct.
Which then becomes the perfect weak link, the pathway for a crack to follow easily.
That is precisely the conclusion for the Fumasi alloy in this study. The TME is due to the formation of this specific intralath cementite, resulting directly from the decomposition of retained austenite.
Interesting.
And interestingly, they also noted that an earlier stage carbide, sometimes called epsilon carbide, was not the problem here. It was the formation of the more stable cementite phase that proved destructive in this case.
That really is a beautiful piece of metallurgical detective work. Okay, let's talk about the final act then, the actual fracture. How does that microscopic cementite film translate into a large catastrophic failure when the steel actually breaks under load?
Right, so now we shift our focus to fractography, basically. analyzing the surface of the broken steel sample,
Looking at the broken pieces.
looking closely at the broken pieces, and specimens that were tempered right in that TME danger zone, especially when they were tested under stress at cold temperatures. They exhibited classic cleavage fracture.
Cleavage fracture, that's the really brittle kind, right? Where the crystal structure basically splits cleanly along specific crystallographic planes, defines brittleness.
Exactly. It's a very planar, highly brittle failure mode with very little energy absorption, very little plastic deformation before it snaps.
And the key observation.
The key observation was this. When they looked closely at the fracture surface using microscopy, both the main primary crack path and the internal secondary cracks that formed ran almost perfectly parallel to the direction of those original martensite laths.
Wow. So the crack isn't just wandering randomly through the material.
Not at all.
It is specifically following the structural lines defined by those laths, where the cementite films are.
Precisely. This microstructural observation confirms it. It shows that those newly formed cementite films are providing the nucleation path, the initiation point, and essentially the easy road for the crack to travel along.
So the crack starts, and instead of having to fight its way through the tougher martensite structure,
It just follows the path of least resistance, which is the brittle cementite film sitting right there at the lath boundary. It directly links that microscopic structural change, the cementite film formation, to the macroscopic brittle failure mode.
okay, this research provides a really rock-solid explanation for TME in that specific PHEMOS alloy. Retained austenite instability leads to cementite film formation, which leads to brittle failure. But this raises the big question for materials designers, doesn't it? Does this specific mechanism hold true for all low-alloy steels that show TME? Or is metallurgy, as usual, more complicated?
Hey, well, as usual, the answer is that metallurgy is significantly more complicated.
Top 5 thing.
Yeah. The later parts of this study are fascinating because they introduce two contrasting alloys. And these prove that while the result, brittle fracture linked to intralath cementite, seems consistent,
Okay.
the cause, the trigger that creates that cementite, can vary dramatically based on the specific alloying elements used in the steel.
Okay, tell us about these contrasts. What changed when they swapped out the molybdenum, for example?
All right, let's look first at an iron vanadium carbon alloy, or FeVzC. This alloy also clearly exhibited TME, no question about that.
Right.
But the researchers found evidence suggesting that the retained austenite, that 5% film we focused on in the Mohs steel, had actually decomposed completely at a much lower temperature, somewhere around 290 degrees C.
Hold on. So by the time the steel reached the 300-plus degree C range where embrittlement was peaking, the original trigger from the first steel, the RA decomposition, was already finished. It was gone.
Correct. It was already over. Therefore, the TME effect observed in this FeVzC alloy could not be primarily related to retained austenite decomposition.
So what was causing the cementite precipitation in this case?
It was attributed mainly to the decomposition of the supersaturated martensite itself.
Okay, we need to define that term too.
Yep.
What is supersaturated martensite, and why would it decompose and form cementite at this temperature?
Okay, think back to the quenching process. When the steel is cooled incredibly fast, the carbon atoms get trapped inside the martensite crystal structure.
Right, they don't have time to move out.
Exactly. The structure holds way more carbon than it comfortably wants to at lower temperatures. It's highly supersaturated, like a sponge completely overloaded with water.
Gotcha.
Now, when you temper it, when you heat it up, especially into that 300 degrees C range, those trapped carbon atoms gain enough energy to start moving out. They precipitate out of the martensite lattice to form carbides like cementite.
Relieving the supersaturation.
Precisely. And in this FeVzC alloy, that process, the carbon coming out of the supersaturated martensite, was identified as the primary driver creating the damaging intralath cementite, leading to TME.
Yeah.
Not the leftover retained austenite.
Wow. Okay, that is a fundamental difference in the trigger mechanism.
Yes.
Same result, cementite films, brittleness, but a totally different starting point.
Exactly.
What about the third alloy they looked at?
The third one was an iron manganese silicon carbon alloy, FMAIC. This provides yet another angle.
How so?
This alloy contained very, very little retained austenite to begin with, less than 2%. Almost negligible.
Okay.
Yet TME was still definitely present. It still showed that characteristic dip in toughness.
Yeah, the cause.
Well, unsurprisingly, with so little retained austenite available to decompose, the TME here was also primarily attributed to that intralath cementite precipitation coming from the decomposition of the highly supersaturated martensite, similar to the vanadium steel.
Okay, so this is the massive takeaway here, isn't it? The structure that ultimately fails, That brittle cementite film acting as the easy fracture path, the cleavage path that seems to be the common thread across all three alloys.
Yes, that's the structural weapon, if you like.
Right, the weapon is consistent, but the chemical trigger that creates that weapon varies completely.
Absolutely.
In the molybdenum steel, it's the decomposition of unstable retained austenite films.
Correct.
But in the vanadium and the manganese silicon steels, it's the carbon coming out of the supersaturated martensite matrix itself.
That's the conclusion. It's a perfect illustration of why alloy design is just so complex and, frankly, so fascinating. You're constantly balancing these competing instabilities.
How so?
Well, you might add an element like molybdenum because you need certain properties it provides, maybe high temperature strength or hardenability. But that same element might also inadvertently increase the stability of retained austenite, making sure that Ra sticks around long enough to decompose right in that critical 300 C tempering range, precisely where you least want that reaction to happen.
You solve one problem and potentially create another.
That's the game in materials science a lot of the time.
Okay, let me try and summarize this for you, the listener. TME, tempered martensite embrittlement, teaches us that tempering steel isn't just a simple linear path to making it stronger and tougher.
Definitely not.
There's this necessary structural weakness, almost a dangerous window. You have to find the perfect balance. You might want a high tempering temperature overall for strength and toughness,
Right.
but you absolutely have to avoid that critical mid-range around 300 degrees C where these microstructural instabilities kick in.
Whether from retained austenite or from supersaturated martensite decomposing.
Exactly. Because if you temper in that window, you inadvertently create these brittle cementite films. You're essentially building an easy fracture road right through the middle of your supposedly high-strength material.
Well put. And that fragility, dictated by features so incredibly small they require powerful electron microscopy just to even see them, it really highlights the absolute necessity of extreme precision in engineering these materials.
It really does.
And maybe the final provocative thought for you to mull over is this. Knowing now that the specific mechanism causing TME varies so critically based on tiny differences in alloy composition and the resulting phases like retained austenite, how much variability in even tiny amounts of Ra, say between 2% and 5%, can we truly afford when we're designing critical high-strength steels?
So yeah, for industries like automotive, aerospace, where failure is not an option.
Exactly. The stability or instability of that last few percent of retained austenite could literally be the difference between a component that performs reliably for years and one that suffers a sudden brittle failure. It forces us to think very carefully about controlling not just the major phases, but these minor residual ones too.